Hey everyone. Over the last couple of lectures we've been talking about polar curves, and in particular we did some hard work on figuring out how to sketch polar curves. Now what we want to do, now that we're able to actually do the sketching, we would like to talk about the area associated with polar curves. So let's say if we have a polar curve, let's say if R is the region bounded by it, the polar curve, say R equals f of theta, and the rays, theta equals alpha and theta equals beta, then the area of R is, and let's write the formula up here, so A of capital R equals 1/2 times the integral from alpha to beta, and then you take the equation for the polar curve, so that'd be f of theta, you square it d theta. Right, so this gives us a formula for computing the area. And let me give you a picture of what we're talking about. So we have the ray theta equals alpha, right? So that angle right there is alpha. The next one, the angle, I don't want to crowd my picture too much, but so that total angle right there is beta. Not just this portion right here, but the entire thing, right? So that entire part. And then we have some polar curve, R equals f of theta. So the region that we're talking about, R, is this shaded stuff here, right? It's bounded by the polar curve and the two rays, right? Theta equals alpha and theta equals beta. And if you want to find the area of R, this formula right there, that integral computes it for us. All right, so now I want to just do examples for the rest of the day. That's all we're going to be doing is examples. So first example, let's find the area enclosed by the cardioid R equals, we're going to do R equals 1 plus cosine theta. And I just want to do the part in the first quadrant. So let's draw the picture now. The cardioid, we've already drawn this one right here, right? It has this heart shape like that. And then we just want the portion in the first quadrant, right? So I'm going to follow this formula right here. And so what we're going to get is that the area equals, so let's see, if we want to be in the first quadrant, then we're going to go from theta equals 0 up to theta equals pi over 2. So we'll have 0 to pi over 2. Then we take our polar curve, that's a 1 plus cosine theta, square the result, d theta, there's the integral that computes this. Now, one thing to notice, our polar curves typically involve cosine and sine. Notice that we square things, so what's going to show up in a lot of these integrals is sine squared and cosine squared. And so I'm going to write it down in just a minute. We need a couple of identities to allow us to integrate those. So hopefully you remember this from Math 142, but I'm going to remind you. So the identities, you probably should put this somewhere, identities that you need whenever you're integrating sine squared or cosine squared, you use these identities. So cosine squared theta, that's a 1/2 times 1 plus cosine 2 theta, and sine squared theta is 1/2 times 1 minus cosine 2 theta. So if you make use of these two identities right here, or you will need to make use of these identities when you're doing these kinds of problems. So I'm going to carry this one out here. So this is integral from 0 to pi over 2, 1 plus 2 cosine theta plus cosine squared theta d theta, so I just FOILed this part out. Now I've got a cosine squared. I'm going to apply this identity right here. So that'll be integral from 0 to pi over 2. 1 plus 2 cosine theta plus 1/2 times 1 plus cosine 2 theta d theta. And so now let's simplify things a little bit, and then we'll be able to just compute the antiderivative. Oh, and you know what? I completely forgot my 1/2. Sorry. 1/2, 1/2, 1/2. And so we'll have 1/2 integral 0 to pi over 2, 3/2 plus 2 cosine theta plus 1/2 cosine 2 theta d theta. And now we're actually ready to compute the antiderivative. So let's see, we'll get a 1/2, and then we'll have, so this is going to be a 3/2 theta plus 2 sine theta plus 1/4 sine 2 theta, and we're going from 0 to pi over 2. Now we plug in our limits of integration, so we'll get a 1/2. This will be a 3 pi over 4 when I plug in pi over 2, plus sine of pi over 2 is 1, so this will be a plus 2. And then we'll have, let's see, this will be sine of pi, which is 0. And then when we plug 0 in, we'll get 0 all the way through. So this is going to come out to be 3 pi over 8 plus 1. Okay, so there's the idea. And so now I just want to do a few more examples. Some of them more complicated now. Right, but they're all going to involve the same formula. So let's see, next one. Let's find the area enclosed by one leaf of the 4 leaf rows. And this one's going to be r equals cosine 2 theta. Now, we already sketched this one, so I'm just going to re-sketch it without going through the process. All right, so remember this one looks kind of like a 4-leaf clover. And so we want to find the area enclosed by one leaf. So we could choose this one if you like. Sorry, I didn't make this very symmetric looking. And actually, that's the point here, is what I want to do, and this will be sort of a common theme when we're doing these types of problems, we want to take advantage of symmetry. And so here's the idea. I've chosen that leaf right there, but in fact, what I'm going to do is just find the area of the top half and then double the result. Right? So, the area, I want to double the result of finding the area of the top half. So that will be 1/2 times the integral, and now really the only question is, okay, what are my limits of integration here? Well, we're going to go from 0 to when it closes up, and it closes up, right, at an angle of pi over 4. That's really the main game when we're doing this, is figuring out what the appropriate limits of integration are, right? So double the area of the top half, that's going to be integral from 0 to pi over 4. And then we will take cosine, and I'm going to square that, so it'll be cosine squared 2 theta d theta. If you want, you don't have to use symmetry. If you want, you could find the area. So this is actually, one way to do this would be to go from minus pi over 4 to positive pi over 4. That would give you the whole thing. But oftentimes, symmetry makes the computation a little bit similar, or simpler. right? And so what do we have now? So this is going to be integral from 0 to pi over 4, because I just have the 2 and the 1/2 cancel. Now I need to apply the identity to cosine squared. So that's going to be a 1/2 times 1 plus cosine 4 theta d theta. And now we're basically ready to integrate, although we pull the 1/2 out first. So that'll be a 1/2 integral 0 to pi over 4, 1 plus cosine 4 theta d theta. All right, so this will be a 1/2 times, when I compute the antiderivative, we get a theta plus 1/4 sine 4 theta. And we go from 0 to pi over 4. Now plug in the limits of integration, and so when I plug in the pi over 4, we'll get a 1/2 times pi over 4 plus, let's see, when I plug a pi over 4 here, I'm going to get sine of pi, which is 0. And then when I plug in 0, we'll get 0 all the way through. So in the end, what we get is pi over 8. All right? So the area enclosed by one loop, right, is equal to pi over 8. Do a few more examples still. So the next one, let's find the area enclosed by r equals 2 minus sine theta. Now, this is a curve that we have not done yet, so I'm going to sketch it. I'm going to go through the process of sketching it because I need to know who my limits are, right? The limits of integration often come from, or usually come from understanding the sketch. So let's see, this is a sine curve that's been flipped upside down, that's the negative, and then raised up 2 units from that 2 right there. So let's see, so let's say 1, 2, 3. So it's going to be an upside down sine curve. So that's at pi over 2. That's at pi. The top point there is at 3 pi over 2. And then 2 pi's right there. That's a 1, 2, and 3. Okay, so now let's sketch this in the xy plane. And so let's see, when theta equals 0, we start at distance 2. When we get to pi over 2, we need to be at distance 1. And then it goes back out to 2, and then all the way out to 3. So it's going to look like that. And so now we can see, right, we want the area enclosed by the entire curve. So we're going to integrate from 0 to 2 pi all the way around, right? And so the area is going to be a 1/2 integral 0 to 2 pi. And then we'll have 2 minus sine theta, all of that squared d theta. I don't think you really need to see me integrate this. Maybe I'll do this one. I'll do one more, and then I just want you. I'll just set up the answer or the integrals for the next 2 examples. So this one's going to be as integral, or 1/2 integral from 0 to 2 pi. We'll have a 4 minus 4 sine theta plus sine squared theta d theta. That's a 1/2 integral 0 to 2 pi. 4 minus 4 sine theta plus 1/2 times 1 minus cosine 2 theta d theta. So that'll be a 1/2 integral 0 to 2 pi just going to clean things up a little bit. So this will give me a 4 plus 1/2, so that's 8 9/2, minus 4 sine theta, minus 1/2 cosine 2 theta d theta. And now we're ready to compute the antiderivative. So that'll be a 1/2, and then we'll have 9/2 theta plus 4 cosine theta minus 1/4 sine 2 theta, and we're going to go from 0 to 2 pi. Okay, so this is going to be a 1/2. So now I'm just plugging in the limits of integration. And so we're going to get, let's see, that'll be, when I plug in 2 pi, we'll get a 9 pi. Plus, when I plug 2 pi into cosine, that's going to give me a 4 times 1, so plus 4. When I plug 2 pi into sine 2 theta, that'll give me a 0. And then plugging 0 will give us 0 all the way through. And so this will be a 9 pi over 2 plus 2. I don't care a whole lot about the actual answer. I mean, whatever that means, 9 pi over 2 plus 2. But I will be very concerned with 2 things when it comes to quizzes or exams. Setting them up correctly, in particular finding the correct limits of integration. And then doing the computation correctly, right? There's some integration techniques that you learned in Math 142 that you're going to need to bring to bear, right, when it comes to computing these integrals. Okay, so now let's do a couple of slightly more complicated ones. And in these ones, I'm just going to set them up, and I'm going to assume that you'll know how to compute the integrals. So let's find the area inside r equals 2 cosine theta, outside r equals 1. Okay, so this one, you know, there's a little wrinkle here. So we've got 2 different curves, and we want to find the area contained inside one, outside the other. We've seen both of these graphs before. R equals 2 cosine theta. That is a circle of radius 1 that's been shifted over 1 unit. So there's that one. And then r equals 1, that's a circle of radius 1 centered at the origin. So now we want the area inside the first one, outside the second one. So we're looking for the area of that region right there. What I'm going to do is I'm going to make use of symmetry. I'm going to find the area of the top half and double it. And so what I need to do is, I mean, think of it this way now. I'm going to find the area enclosed by the first circle, the outer circle, and then subtract away the area enclosed in the second circle. Right? So this should remind you of just, you know, a typical calculus problem. To find the area bounded by 2 curves, you just subtract. And so I need to know that intersection point so that I know the ray of where to stop my integration. So I'm going to set these equal to each other. 2 cosine theta equals 1 means cosine theta equals 1/2, which means that point right there is theta equals pi over 3. So the area is going to equal 1/2 integral. Oh, and I'm going to double it, right? So it'll actually be 2 times that. So 2 times 1/2 integral 0 to pi over 3. The outer curve is 2 cosine theta. So we're going to square that d theta. And then I'm subtract away the area contained by the inner one. So that'll be a 2 times 1/2 integral 0 to pi over 3. And then we'll have 1 squared d theta. All right, so if you compute this, that will give us the total area right there. Okay, so it's a fairly easy integral to compute. This is straightforward. I hope that you understand the setup. Now let's do one more kind of similar thing where we'll have two curves involved. So let's find the area enclosed by, so this needs to be inside both. So let me word this a little bit better. So find the area inside both r equals 1 plus cosine theta and r equals 1 minus cosine theta. Now, we've seen this one right here, r equals 1 plus cosine theta. That's the cardioid that goes like that. And you can check, this one's fairly easy to see. It's a cardioid that opens in the opposite direction. So it's just another heart like that. And so now we want the area that stays inside both of them, which means that we want this stuff together with that stuff. And now, making use of symmetry, here's what I'd like to do. If I could find the area enclosed by one of those, I could then multiply by 4 to get the answer. And so, the one that I've shaded right here, it's contained only inside that curve right there. And so here's the area. Remember, I'm going to multiply by 4, so it'll be 4 times 1/2 integral from, so let's see, when this gets started, that's at 0 to pi over 2. And then we'll have 1 minus cosine theta squared d theta. So notice I don't even need to know the other curve, right? Finding just that 1/4, which is only bounded by the one curve, is all I need. All right, so now we have an easy integral to compute. This is a straightforward computation. And so, remember, the important part here is being able to set this up, which means that you need to be able to sketch the curves, find the intersections so that you can find the limits of integration. And then, typically, you're going to have a cosine or a sine squared. Make sure to apply the appropriate identity to compute the integral. All right, that's good for today, so we will see you next time.